I think we are getting on near 3 o'clock. First, let's start off. Are there any questions? Again, if any of you have cameras you're willing to turn on, I like to see people. If there are any questions about anything having to do with graphs, last class we've been talking about minimum spanning trees. We've been talking a little bit about the shortest paths, which is what I'm going to finish talking about today. And today is going to be kind of my last section on graph algorithms. So if there's anything people want to talk about graph algorithms, now is a very good time to do it. Any questions about anything? Going once, twice. Any questions? Okay, so before I get to the daily problem, I want to make sure people, which I think is actually a very, very interesting daily problem today. But I want us to go and make sure we understand what Dijkstra's algorithm is. We talked last time about shortest paths. The idea of Dijkstra's algorithm was basically we were going to grow a shortest path spanning tree from starting from some node, okay, and it's going to find the shortest path basically to every node in the graph, okay, and it's a little like it's a lot like Prim's algorithm in that at each point we're going to have at any given moment in the graph evolution, we've got some partial tree that we've built. We're going to add one new vertex that we know the shortest path to, and that's going to be my shortest path spanning tree. I know a way to get to here at a cost of 11. I know a way to get to here at a cost of 11. Okay, actually, if that's the cheapest way to get to I know how to get here at a cost of 10. That's the best of my options. I am now going to grow my tree out here and my fringe, okay, my window of things that I consider next. I am slowly going to build one step at a time a tree of discovery or inclusion into the shortest path tree. And I am going to find the nearest neighbor from the shortest path from my vertex A to every other node in the tree. Does everybody see that this tree gives me the shortest path from A to everybody else? Okay, any questions about that? Does everybody see that it smells like Prim's algorithm in what it's doing? The only difference was really what edge did it choose next? Any questions about that? Okay, now let's get a little bit trickier, okay? In Prim's algorithm, if I do start Prim's algorithm from a different node, will I end up with a different tree? Yes or no? What do people think? Prim's algorithm, minimum spanning tree. I start a Prim's algorithm from a different node. Will I end up with a different tree or the same tree? Any ideas?
You could potentially have a different one. The minimum spanning tree isn't necessarily unique.
Okay, so you're telling me that the minimum spanning tree is not unique, so there's no reason why I couldn't find a different one. And you're right. Now, suppose I have every edge in the tree, every edge in the graph has a different weight. So there's no duplicates. Now, if I did minimum spanning tree from two different vertices, would I end up with the same, the same edge weight? Would I end up with the same trees? Now I'm seeing nodding, yeah, right, okay. Now, suppose I start the shortest path spanning tree from one vertex. Okay, this is going to give me the shortest path from A to every other node. If I find what you call it, if I instead did a shortest path spanning tree from a different node, would I find the same tree? Okay, any opinions on this kind of a matter? Who here says yes? Who here says no? Nothing bad's going to happen to you if you get it wrong.
Well, I would say no.
No. Why not?
Because you can potentially have a path which has multiple edges. Say you have the path between this purple node that you have circled and the one beneath it. The edge of weight 2 is currently the shortest path. But if you increment, or I should say, imagine that like the path to the one to the left of it is actually the 2 and the 2.
Right. So the next,
So
if we did Dijkstra's algorithm from here, the next most desirable thing, you're like the edge of weight 2. The weight 2 is exciting because there's a path of weight 4 to here, right? It's not that the edge of weight 2 is so exciting. It's at the cost of getting to here at a cost of 2, and that getting to there, the fact that I can get to here at a cost of 4 is exciting. Does everybody see that this is kind of already wildly different than the previous spanning tree? Okay, that's because the shortest way to get from here to every city in the country is not going to be necessarily the shortest way to get from any city in the country to any other city in the country. So no, the shortest path spanning tree tells me how to get from me, the shortest path from me to anybody else. But on the other hand, the shortest path from a vertex to some other vertex need not care about that. You could imagine, just if we're going to take a look at something like this. Suppose there were roads of length 1 going out to here. Roads of length 1 getting out to here. And a distance 2 from here to here. The shortest path from me to every vertex is going to be these. The shortest path from this to any vertex is going to certainly include that direct edge. So the shortest path spanning trees, it's important where you start from. Dijkstra's algorithm tells you the shortest path from A to everybody else. Any questions about that? Do people kind of believe that? And what was the algorithm again? I want to make sure people see this before we get any cleverer. Dijkstra's algorithm, let's now show it in its glory, not like it's pseudo prims. Okay. We have a tree of discovery. Okay, a tree, shortest path 3 telling me the shortest path from me to every other vertex. Originally, to get from start to anybody else costs an infinite amount, and we don't know how to get there. Okay, the start vertex, we know we can get there at a cost of 0 and starting from start. Then, while V, the last vertex I have picked, if that's not already in the tree, put it in the tree, and then go through all its external edges, okay, and see if we can find a better way to some vertex that is not in the tree, okay? If the best way I know of so far to get the W, okay, was that, but there's a way from V to get from the start to V, and then from V to Y or W, okay? wait, if W is the destination here, if I have an edge EW, okay, an edge VW, what I want to know now, if the best way to get the W before is bigger than the cost of getting to V plus the edge from V to W, then I found a better way to get there, and that I have to update. For minimum spanning tree, all I cared about was the weight of the edge. So for prims, I didn't worry about the distance here, not on this side. But here, the value of an edge is a function of what it costs to get to that vertex plus the cost of the final hop. This tells me the cheapest way to get to every vertex. In each iteration, I am using the vertices that are already in the tree. Then I'm going to go figure out what's the next vertex to get in the tree by finding the vertex that's not in the tree that is the cheapest one that is closest to the start. And then I'm going to keep doing this n times, and that's going to do the thing. Any questions about Dijkstra's algorithm, why it works, okay, what it does, what the running time is? In fact, that's a great question. What is the running time of Dijkstra's algorithm? Okay. What was the running time of Prim's algorithm? Anyone remember?
N squared.
N squared. And what have we changed? We have changed this thing, right? It used to be something that probably looked like this if I didn't know better. Okay. Has that changed the running time? We added a constant amount of an additional addition step twice. Okay, inside an inner loop. Is that going to change the big O running time? Absolutely not. So this is still an n squared algorithm. And I don't really want to go through it. If you use some fancier, that's basically just saying what I said here. There are some fancier ways to implement it faster using, let's say hotshot data structures. Okay, again, just like we saw before, our basic steps are going to be find the minimum vertex in the fringe, which is a heap-like thing, okay, and update it when we find closer ways of to a vertex, change the value in the heap. That latter operation is not supported by the kind of heap that we normally do. But there are fancier data structures. In fact, you can do it faster. This is why the fact that there is faster algorithms for finding the shortest path is why Google's quite happy to tell you the cheapest way to drive between here and Bolivia. Because if it was n squared, it would be a really big computation. Any questions about it? Okay, any questions about finding shortest paths? Okay, Dijkstra's algorithm, why it's a good thing. Okay, what I'd like to do is now talk about the problem of the day. This, I believe, is, actually, is this the problem of the day? Okay. Actually, tell me if this is the problem of the day. It isn't actually what I thought it was.
Yeah.
Yes, okay, so then now let's say, actually, I'm a little bit different. It's not a great problem, but it's good to do, okay? Let's take a look at this thing. It says, what does it read? It says that we're given a directed, an undirected weighted graph. We've got the shortest path spanning tree from V to everybody else in the graph. Ka-chunk, ka-chunk, ka-chunk. Now, every one of the edges is increased by a constant, K. Okay? Is T still the minimum, the shortest path spanning tree? Okay, did everybody kind of get that idea? I have found the shortest path from V to everybody else. Now I add a certain amount to every edge, the same amount to every edge. Is that going to still be the shortest path spanning tree? Who here says yes? Who here says no? I think I'm seeing yeses and nos. Okay, so I don't think a yes or a no is good enough. It looks like I need either a proof or a counterexample. If it's a no, then you should show me why it isn't true. Can anybody give me an example of a graph where this isn't true? I'm seeing 3 vertices. That's not quite a graph. Anyone want to describe this? Can anybody make a graph where, in fact, you could add something the same amount to the edges and what the shortest paths are changes? Okay. So I think I want something that goes ka-chunk, ka-chunk, ka-chunk. That's 3 vertices, right? What if I had a edge here that was 1? What if I had an edge here that was 1? And what if I had an edge here which was 3? And I want to go from S to T. What is the shortest path spanning tree from S for this graph? If I want to describe the shortest way to get from S to everybody else, what would that tree look like? Okay, I think it would look like this. Does everybody agree? This tells me the shortest way to get from S to everybody else. Now, what happens if I bop each one of these edges up by what? If I increase all the edges by 1, the shortest path spanning tree is unchanged, right? But what if I increase every edge by 2? 3, 3, 5. Now what does the shortest path spanning tree from S look like? Okay. Does everybody see that? The topology of the tree has changed. Okay. When you add the same amount to every edge. Does everybody kind of see that? This is one that's important to see. This is not that hard. Okay, so if you don't see this, this is a good question like I didn't understand. Any questions about that? Gets at the heart of what is a shortest path spanning tree. Any questions? What about a minimum spanning tree? If we took a graph and we add the same amount to every edge in the graph, does the minimum spanning tree change? The cost of the minimum spanning tree will presumably change, but the question is, does the tree itself change? If I had what was a minimum spanning tree, is it still a minimum spanning tree? Right? So if I had a graph like this, is the minimum spanning tree of this graph the same as it was before, right? If we looked at the minimum spanning tree, let's make it what color do we like? This thing. What was the minimum spanning tree before? It would have been the 1, 1, right? That would have been the minimum spanning tree of it. When we bopped up the edges, the minimum spanning tree still is 1, 1. Is the minimum spanning tree going to change if we add the same amount to every edge? I need either a yes, not just a yes or a no. I need a proof or a counterexample. Does anyone want to give me an argument why or a counterexample? Okay. You still choose the same edges with prim or Kruskal. What I will say is, certainly with Kruskal's algorithm, what does Kruskal's algorithm do? Kruskal's algorithm sorted the edges from cheapest to most expensive and added them in the order, unless they created a loop, right? Unless it created a cycle. When you sort the edges after I add the same thing to it, okay, will they be added in the same way? I will claim that the sorted order is not going to change when I add the same amount to every edge, right? Does everybody agree with that? So if I go and pull them in, okay, Kruskal's algorithm is going to do the exact same thing. It's going to pick the exact same edges, even if you add the same amount to all the edges. Does everybody kind of see that? That I'd like to hear nodding about, or if not, an explanation, a question of why. So for Kruskal's algorithm, I understand that, and that to me is a proof that it's going to be unchanged when I add the same amount to every edge in a minimum spanning tree. The argument of whether I can do that with prims, it seems to be a more complicated thing to argue that that's true. Okay, it presumably is true because Prim's algorithm is is also correct, but that's less obvious to me. But from Kruskal's algorithm, it's clear that that's right. Any questions? Now, what if I take a graph? Let's play this a little bit more. I want you to think about this. What if we, take a graph and we multiply all the edges by a weight? Okay. Now, will that change the shortest path spanning tree? Let's think about it. Can I get this idea? Suppose I take all the edges in a graph, multiply them by the same weight. Will that change what is the best way to get between me and somebody else? Any ideas? I hear I don't think so. Can we formalize why that is? Okay, because it's proportional. Well, I guess one way that you're thinking about it is, what happens when I convert a distance from feet to meters? You guys are experts on the metric system. What do I got to do to convert something from feet, measuring something in feet, to measure something in meters? What do I got to do? How do you convert between feet and meters?
I don't know the exact number, but it's just multiplying by some value.
Something like that. Is the shortest path for something, if I was talking about the shortest path from me to you as measured in feet, is it going to change when it's measured in meters? Obviously not, right? So that's kind of an argument that kind of multiplying everything by the same thing is not going to change the shortest path. Does everybody kind of see that? Okay. And again, you would probably have to, I think that, to me, that's a convincing proof, okay? Maybe even more convincing would be to kind of show that the algorithm is going to do the exact same thing, okay, as it did before. So what else is it? What if I did what if I took a graph and I multiplied every edge by the same amount? How would that change the minimum spanning tree?
No, you can make the same argument that you did when you were just adding.
Exactly right. The
numbers.
Kruskal argument is what we have. The Kruskal fact is that if we did Kruskal's algorithm, if we had them multiply all the numbers multiplied by 2, the smallest one is still the smallest edge, the biggest edge is still the biggest edge, okay? They're still going to be in the exact same order, and inserting them will still not create cycles. Will or will not create cycles, just as before. Does everybody kind of see that? So in fact, multiplying everything by a constant will not affect the the shortest path, the minimum spanning tree. Any questions about that? I think these are good exercises to work through what a the minimum spanning tree and what the shortest path spanning tree are doing. Any questions on finding shortest paths? Going once, twice. Okay, so I would like to show you another algorithm for finding shortest paths. That is, it's an algorithm that's better at solving a variant of shortest path, which is the all pairs shortest path problem. We saw with Dijkstra, we found from any vertex S, we found the shortest path to every other vertex. Sometimes you are interested in building a table for each vertex from I to J, from 1 to N and 1 to N. What is the length of the shortest path from I to J? So for every pair of vertices, you know how far apart they are. If we ran Dijkstra's algorithm, we're going to figure out what's the distance from vertex 1 to all other vertices. It should be clear that if we wanted to find the shortest path distance between every pair of vertices, we could run Dijkstra's algorithm n times, each time filling in a row of this matrix. And since Dijkstra's algorithm took n squared, n times running Dijkstra's algorithm, we could get the whole table in n cubed time. Any questions about that? Why do you want sometimes to find the shortest path between every pair of vertices? Well, there are a lot of reasons why that's kind of a cool thing to know. One thing that I think is compelling might be in if you wanted to know, let's say, if the you were sending messages, if this was a network, and you wanted to know what's the longest travel time across this network. You'd want to know which pair of nodes are furthest apart. That's kind of like, you know, find that the one with the longest, shortest path is kind of the ends of the network. It's kind of a diameter of the network, we would call it. And that's kind of a useful thing. And if you have this matrix of all the distance from I to J for all pairs, this is a useful thing to know. Okay? Any questions? Let me show you an amazingly slick algorithm for finding the all pairs shortest path matrix. Okay, and this is going to be a flavor of something we're going to, this is an example of a type of algorithm we're going to spend 2 weeks on in a little bit, okay, called dynamic programming. Dynamic programming is an idea of using a recursive algorithm or recurrence relation to try to figure out what to solve something. Those of you who took what you call it, well, let's remember what a recurrence relation is. How many of you have taken AMS 301? If some of you taken it, I can see some twitching in the screen. Some of you may have taken it. You know about Fibonacci numbers, right? I think you know that the nth, and we'll talk more about this soon. So if you don't know about it, don't get too nervous. Does everyone remember that the nth Fibonacci number was the sum of the 2 previous Fibonacci numbers, right? So what were the Fibonacci numbers? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Does everybody see how I'm doing it? And the reason I'm doing it is this number here is going to be the sum of this plus this. And if I build them in sequential order, I can use this recursive equation to tell me quickly what the next value. What's the next value? 89. Okay? Any questions about that? The idea of this recursive algorithm for finding Any questions about that? How many people have seen these kind of recurrence relations? Okay. There is this idea for an algorithm that is going to be amazingly simple once you see it, but is maybe a little bit tricky to understand till you do. Okay. And what we're going to do is to build our shortest path matrix, D, okay? And we're going to basically come up with what is the length of the shortest path from I to J using certain vertices as intermediates. What is the shortest path? If I have a vertex I in a graph, what is, and a vertex J in a graph, what is the length of the shortest path from I to J that uses no intermediate vertices? Okay, this is a simple question as a point of being dumb. Okay, if I give you a graph and I want to know a weighted graph, and I want to know what the length of the shortest path from I to J that doesn't go through any intermediate edges.
The edge between them.
Vertices. What is the length of it?
The edge between them.
The edge between them. And what if there is no edge between them? What's the shortest path to get between me and London with no intermediate edges between it to drive?
Infinity.
Infinite. I can't drive to London, right? I can drive from here to, maybe down the end of the block without making a turn, but that's about it, right? So Dij is going to be the cost of gutting from I to J with no intermediate vertices. If I is equal to J, I can do it at a cost of 0. If there is no edge from I to J, it's going to cost me infinite. If there is an edge, well, that's the shortest way to get from I to J without any intermediate vertices. Does everybody see that? This is pretty much by definition. The question is, can we update this matrix where we allow vertices to be in the intermediate? Okay? That's going to be kind of now the idea behind this particular algorithm. How would we do it? Well, there is a, an algorithm called Floyd's algorithm, okay, which basically is going to say, number all the vertices from 1 to n. That already kind of happens. Let's let Dij raised to the k be the shortest path from I to J using only vertices from 1 to k as intermediate vertices. Okay? Somebody's got family in the background, so maybe quiet that down. Okay, what else do I see here? We saw that when, as I said before, if I'm not allowed to use any intermediate vertices, this basically weight matrix that I talked about here, this was the optimal way of doing it. Does everybody agree? Now, what is the distance from I to J where I'm allowed to use vertex 1 as an intermediary? Can anybody figure that out? If I'm only allowed to go through vertex 1 as an intermediary, what is the distance from I to J? Can anybody come up with an expression? If it's recursive, it should be in terms of things like this. Any ideas? What is the cost if I don't use anything as an intermediary, where I have a direct edge? What would that be?
The weight of that edge.
The weight of the edge, or since I want a recursion, wouldn't that be Dij sub 0? That's what it means, right? What if I want to now find the shortest path from I to j, where I use 1 as an intermediary? What would that be?
I could say di1 to 0
Okay.
plus d1j to 0.
Okay. It looks like you, so what are you saying? It'd be d of what?
di1,
What
I
I
comma
think I
1.
want to do is something like this. I claim it's dik 0 plus k edge kj. Let's think if this is right. If I want to get to, what you call it, I to j, oh, using just 1 as my intermediary, right. What is the story? That's exactly true. I've got my only choice here is this is 1, and this is 1. Let's look at that. Does everybody see that if I'm allowed to only use 1 as an intermediary, okay, which is cheaper? And what would I do? It's the cost of getting from I to 1 without using anybody as an intermediary, plus the weight of the edge from 1 to j. Does everybody kind of agree with that? This is how much it would cost if I make a detour through 1. This is one where it doesn't. Everybody agree that those are the only two possibilities here? Any questions about that? Which of these is cheaper? Going directly or going through vertex 1?
I don't think we can tell.
Can't tell, okay? But we want the cheaper way, so how are we going to do it? What if we explicitly take the minimum of these two things? Does everybody see that this is now right? Okay? The cheapest way to get from I to j, we were allowed to go through vertex 1 and vertex 1 only as an intermediary, would be either we don't bother going through 1 or we do go through 1. Does everybody agree with that?
I have a question.
Yeah.
What if you were to assume that the triangle inequality is in place here? Then you would know right away that it's better to go directly, right?
Well, you're saying if there's a triangle inequality, you know it's better to go directly. Now, are you allowing edges? But recognize that strict triangle inequality is a pretty unusual graph. Okay. If you want to find the shortest path from here to that place in Bolivia that I keep talking about, is there a direct edge from here? I mean, we agree if I had a plane and that place in Bolivia had an airport, okay, I could fly directly there, okay? But generally speaking, the triangle inequality holds for points in the plane. It doesn't hold for road networks. Road networks are, for example, not typically complete. Do you kind of agree with that? So we agree that if, in fact, the triangle inequality holds, the shortest path between any 2 points is as the crow flies. Okay? But that's not really the case for most interesting shortest path problems, right? Okay.
Got it, thank you.
Okay. Any questions? Okay. So if people got this, actually, this may make better what Floyd's algorithm does. But let me just make sure I show you what Floyd's algorithm is going to do. This is the entire algorithm for Floyd's algorithm. And as you'll notice, the key step here is basically just a generalization of what I was just showing you. Okay? What is the idea? We're going to start out the shortest path between any, build that matrix, which we saw was easy, was like a basis case. The shortest path from any vertex to any other vertex where nothing was an intermediary. This was basically like the weights on the graph, right? Now, we're going to have an outer loop that's going to go around and say, in each iteration, I'm going to give you a new vertex, which can be considered to be the intermediate vertex. Okay? The first round, we were dealing with what k was 1. And when k was 1, wasn't that actually exactly what I got here? That was exactly the same thing that I showed you on the last slide. Okay? Generally speaking, we're allowing k as our intermediate vertex. Now we want to know, for every vertex ij, what is the shortest path, the length of the shortest path from I to j, using vertices 1 through k as intermediaries. We already knew it for k minus 1, and I'm going to claim the shortest path between I and j using vertices 1 through k as possible intermediaries either goes through k or it doesn't. Okay, does everybody agree? If it doesn't go through k, this was the shortest path from I to j using vertices 1 to k minus 1 as intermediaries. This means does not go through j. If it does go through k, what do we know? The shortest path from I to j that goes through k goes from I to k and then goes from k to j. Does everybody see that? We know because we already computed it. The shortest path from I to k using 1 through k minus 1 as intermediaries. We know the shortest path from k to j using 1 to k minus 1 as intermediaries. Does everybody see that if I run this thing, I'm going to find, by the time I get to the end, d sub ij raised to the n is the shortest path from I to j using any vertex as a possible intermediary. That is going to be the shortest path from I to j for every vertex pair of vertices in the graph. Any questions about this algorithm? Okay, this should look a little tricky. It should look kind of weird, but you should see that it's kind of simple. Does this look scarier or less scary to program than Dijkstra's algorithm?
Less.
Less scary. In fact, let's analyze this. You guys are now expert analysts. Okay? You may not feel you're good algorithm analysts, but when your for loops come along, you guys feel big, right? What is the running time of this algorithm here? Okay? This loop is going to go around how many times? It's going to go around n times, right? And how much time is this step going to take?
Constant.
Constant. What's it going to do? Look something up in a table. Look something up in a table. Look something up in a table. Add those two numbers together. Take the min of those two. This is going to be constant. So that's n. What happens if we have an n algorithm going around n times? How much is that going to be?
N squared.
N squared. And how much is this going to be?
N cubed.
N cubed. And here we had the original adjacency matrix. How much is that going to be?
N squared.
N squared. Good man. Okay. So that says that this whole algorithm is going to be n cubed and find the shortest path from I to j for any vertex, pair of vertices. Does everybody kind of see that? Okay. And I want you to think about this. Okay. It's a little bit tricky, but it also, if you stop and think of it, can't be that hard. See how simple the inner loop is? Okay. This is a great example of something called a dynamic programming algorithm, which you guys will suffer through in about 2 weeks. And if you want to understand what this one is, okay, you're going to have a much easier time understanding that. Okay, any questions about how this works or why? Do I need to go through it again? Any questions about that? It should be obvious why it is n cubed. The real question is, can you see why it correctly finds the shortest path from I to j? And do you see the mechanics of it? Here's kind of an example of this algorithm in action. We started out with the adjacency matrix. If vertex 1 is allowed as an intermediary, which is what I think it is here, okay, which vertices, if we have this graph and we have A as an intermediary, where will we be able to find shorter paths between? Which vertices will we be able to find shorter paths between if A is the intermediary of that graph? It's only allowed to use as an intermediary. The only places we can do are the ones that go into A, have a path into A, and a path out of A. BC is what changed. Actually, DC is also going to change, right? There's a new path from D to C through A. So everybody see that these are the cells that changed when we allowed A as an intermediary. What if we now allow B as an intermediary? Okay, that's the next one. Let me clear this up a little bit. Now, if I allow A and B as an intermediary, which vertexes, which pairs of vertices will have a new way to get between them? I'm seeing you like the idea that from B to A, there's a better way to go. Is there any other vertex? I'm seeing from C to A, right? Right? So bingo, that's why that one's bolded. We found a new way of doing it. Now, what if I'm allowed A, B, and C as intermediaries? When I'm allowing C as an intermediary, which pairs can have shorter paths to them? Okay. Anything that goes into C by what goes out of C. So AB can be updated, right? What do we know about actually, a little bit trickier than what I'm saying here. Now when I'm allowing A, B, and C, recognize that C can be used as an intermediary. Now the paths are getting complicated. Any path that goes through C, okay, any vertex path where C is useful. I want to know if is there a better way by going from A to C, and then from X to C, and then from C to Y. If you go through this thing, like here, we're updating B, AB. Why is there a new, better way to get from A to B? Well, the way to get from A to B through C, okay, was actually, I guess, direct. That was pretty easy. Why is there a new, better way to get from A to D? Okay, let's stop to think about it. Why is there now a better way to get from A to D through C? Or actually, I guess that's also pretty obvious. A to C is direct, so there's a way of getting 4. Why is there a better way to get from B to D through C? There's no direct way to get. B is not adjacent to C. Okay, but because we are allowed to use A as an intermediary, we have a way of length 5 of getting to from B to C. There's a way of 6 of getting from B to D because we have a way to get from B to C through A of 5 plus, of course, from C to D. Any questions? I encourage you to work through this and make sure you understand what this algorithm is doing. Any questions about finding shortest path or Floyd's algorithm or any questions like that? Anybody? Okay. Okay, so I do hope you will look at this thing. This, in fact, is the code for Floyd's algorithm. And this, if you look at it, is pretty ungodly simple, isn't it? Okay, take a look at this thing. What's it doing? It's doing the 3 loops that we said. Okay, it is basically saying the cost of going through, the cheapest way of getting from I to J through K is the path length from I to K plus the path length from K to J. If going through K is better than what we know about, update it. Okay, this is the Floyd's algorithm. Any questions about that? Now, Floyd's algorithm is a what you call it? It's often called the Floyd-Warsaw algorithm. Warsaw got out kind of easy by noticing that Floyd's algorithm could solve another problem that's very, very helpful sometimes. Okay? And this is the problem of transitive closure of a graph. Suppose you have a directed graph. It is sometimes interesting to know who can be reached, okay, from a particular node. Okay, so let's just take a look at this. From vertex 3, is there a way to reach vertex 2? Can you get from 3 to 2? Can you
Yes.
get from 3 to 1?
No.
No. Okay. So the transitive closure of a graph says basically, let's build a binary matrix, okay, of where ij is going to be true if there is a path from I to j. Okay. Any questions about that? Okay. It should be clear that we can use what you call it, we could use it to figure out Floyd's algorithm to figure out the shortest, if there is a path from I to j. How would we use Floyd's algorithm to solve transitive closure? Can anybody show me? Floyd's algorithm, remember, gave us the all pair shortest path matrix. Transitive closure is going to tell us something is true if there is a path between I and j and false if there isn't. Can anybody give me such a thing?
If the shortest path is infinity, then there's no way to get from I to J.
The shortest path is infinity, you say it's false, and otherwise you say it's true. Everybody agree with that? How else would you do transitive closure? If you didn't know about Dijkstra's algorithm or Floyd's algorithm, how would you do transitive closure? Any other way of doing it? DFS or BFS? If you start from one vertex, do we agree that either a BFS or a DFS is going to visit every other vertex in the graph, right? So anything that you're reachable, anything reachable from me, I would be able to tell in a breadth first search, right? Now, what is faster, doing n BFSs or doing our n cubed Dijkstra's algorithm, Floyd's algorithm? Which one of these is faster?
I think they're the same.
What?
They might be the same.
They might be the same. Why might they be the same?
I'm just thinking if we have a dense graph, then m would be n squared.
If you have a dense graph, the dense graph, this would be n times n squared. In a dense graph, they are both n cubed. For a dense graph, Floyd's algorithm probably wins because it's such a tight loops and stuff like that. What do you win in a sparse graph? What's the complexity in a relatively sparse graph? This is going to be n times m. Does everybody see that in that case, doing multiple BFSs or DFSs is going to be the win? Okay? Any questions about that? But actually using, being able to tell the component structure of, being able to tell the component structure in a graph is very, is a very, very useful thing. We talked about connectivity before. In undirected graphs, a graph is, connected if it was all in one piece. If not, we were interested in the connected chunks. Notice that when we're talking about directed graphs, okay, the chunks are a little bit different. This graph really kind of has two chunks of vertices, right? One chunk, two chunks. Within this one, there is a a path that, a cycle. So you can get between any of these vertices, drive around legally. But you can't get from, you can get from this component to that component, but not the other way around. Trying to understand the component structure of directed graphs, okay, is an interesting thing. Okay, suppose you want to work in a family tree. Who is a descendant of who? How do I know who's a descendant of who? First of all, is a family tree a tree?
Yes.
You think a family tree is a tree? I don't think so. Well, let's just think about it.
No, because you have like people from two different sides.
Exactly right. We're thinking of family trees. As for you, you have two parents. Okay? Okay, so you have a mommy and a daddy, right? And everybody else has a mommy and a daddy, as far as I understand it. And we're used to this thing kind of being a tree because, but of course, eventually people start marrying each other and it gets more complicated than that, right? If you keep going back, how many grandparents do you have? You have, I guess 4 grandparents. How many great-grandparents? 8. Do your number of great-great-great-great-great-great-great-great-great-grandparents keep doubling if you go back far enough in time? If so, 20 or 30 generations from, 100 generations ago, you would have had 2 to the 100, blank grandparents. There weren't 2 to the 100 people on Earth. Okay, the graph gets to be more complicated, right? But if you want to know whether 2 people are related to each other, that I claim is a transitive closure-like problem. It's about whether or not there's a path between you, whether I'm an ancestor or a descendant. Certainly if we view a tree as a directed thing, ancestor relations. Okay, is one person an ancestor of another? I said, is X an ancestor of Y? That corresponds to, is there a path from you to me in this directed acyclic graph? Presumably in the ancestor relation, unless some weird things I don't know about happen. There's not going to be cycles where, someone's both their child and their grandparent or something like that. Okay? Anyway, for a lot of problems, it's interesting to think about the connectivity structure, the transitive closure, okay, is kind of gets at this idea for directed graphs of graphs having hunks, and within a hunk you can drive freely, but there are sometimes one-way paths between chunks, components. And that's the kind of thing that's captured by transitive closure. Any questions about this? Any questions about graph algorithms? Okay, I'm happy now. I'm here a little bit early. I'm done with where I think I wanted to be today. Okay. Any questions about any aspect of graph algorithms? So I'm going to move on after this.
Wait, I just wanted to clarify, when would you use Dijkstra's versus Floyd?
Well, let's think about it. In Dijkstra's algorithm, it is going to tell you the shortest path from you to everybody else. Floyd's algorithm is going to tell me the shortest path from everybody to everybody else, right? So you tell me, when are you going to use Dijkstra's algorithm instead of Floyd's algorithm?
I mean, if you know that you're starting from a particular vertex.
If I want to find the shortest path from one place to either every place or one particular place, okay, I would use Dijkstra's algorithm, right? If I want to know for every pair of vertices the length of the shortest path, that's a Floyd's thing, right? One curious thing about Dijkstra's algorithm is that to find the shortest path between me and, let's say, a particular place, okay, it implicitly requires me to build the shortest path from me to everybody else in the graph, right? Basically, to find the shortest path between, X and Y, I am going to build the shortest path from X to a lot of other vertices. I guess I can stop the moment I add Y to my tree. But it's kind of a curious thing. In the worst case, I might as well find the distance from me to everybody else instead of between just me and who you care about. Any questions about that? Okay. Will this also be the shortest path from Y to those vertices? Well, if I know the shortest path from X, that's an interesting question. Okay. If I know the shortest path from X to all those vertices, okay, let's say I start doing it. I'm building just like I did here, I build my shortest path thing. Actually, this is a bad draw. I mean, let me draw it a little bit better. So I see, I'm building my tree. This was X. I'm building my shortest path 3. Is this going to now tell me the shortest path from Y to all the vertices in my tree so far?
No.
No, why not?
You'll get a different shortest path tree if you start at a different vertex.
Right. Let's think about it. What's the shortest path likely if this is vertex Z? What is the shortest path likely from Y to Z? If I want the shortest path from Y to every vertex, this edge is probably quite interesting, right? This is the restaurant that's the shortest, this is the nearest movie theater to that bodega in Bolivia I've been for some reason talking about in class every time, right? But if I want to find the shortest way from me to Bolivia, this edge is unimportant. Navigating from here, this vertex is very close to it. That edge is very important, okay? So the answer is no. You're finding the shortest path from one vertex radiating out. Any other questions about graph algorithms on anything else? We talked about depth first search, breadth first search, shortest path, minimum spanning trees, connected components, bipartite, testing of a graph is bipartite, any other kinds of things. Nothing. Okay, it offends me as a professor to end class early. So if not, I'm going to have to talk about something else. Any questions? Okay. We've talked here about how Google is quite eager to find the shortest path for you for free between any two places on the map. Okay? If you think about it, that's kind of an amazing thing, right? And yes, there's a fear. So here we are sitting in Long Island. I guess instead of it, I don't have Bolivia on the map, but let's say I have the end of the Cannonball Run, which is this place in California. Okay? What if I want to find the shortest path from here to here? Do you see that by Dijkstra's algorithm, what is Dijkstra going to do? It's going to find the shortest path to closest places around me. Does everybody see that if we were looking at an animation of what Dijkstra's algorithm is likely going to do, it is finding the shortest paths around here. Maybe it's going to curve out in a front like this. Does everybody see that this is going to require really finding essentially the shortest path probably to just about any place that's closer than this place is, okay? That's what would happen on a map quest if they used, on a Google search, if they used, Dijkstra's algorithm. Does everybody see that? So that's, something like n squared. That's something like, it's, in fact, in order for Google to do this efficiently, there are a lot of optimizations that are done. They don't really necessarily change the worst case running time. But in practice, there are, things you can do. What kinds of things could you do?
You could use like heuristics, maybe like A star or something.
Some kind of heuristics. Again, you're mumbling A star. A star happens to be a heuristic that finds, and sometimes it's a best first search heuristic, right? So, anyone that says, you might very well like explore the highways first, okay, and say, well, look, maybe the shortest path from here to California, there are cross-country roots, okay? And maybe I should explore those and get a bound, okay? And by looking at something like that, that might help, okay? That's a fair thing. Another observation is, if you're here at Stony Brook, okay, here you are at Stony Brook, and we're going to get to California, is there anything that we know about the path from here to California?
Unless we take the ferry, we'll have to go through the city.
There are very few places off Long Island, isn't that right? So, you know, what is it? What are the ways off the island? We can take the Verrazano Bridge. What else can we do? We can go into the city. We have the Manhattan Bridge, the Brooklyn Bridge. I guess you're allowed to take the ferry. I'll let you take the ferry, and there's another ferry out here. Does everybody see that you could pre-compute the shortest path from every place on in Long Island to all of these important edges, okay? And the problem really reduces to find the distance from me to a place off Long Island, which is one of these bridges, plus the shortest path from off this island to to the stuff that's on it. So by pre-computing the distances to these special cut nodes, okay, I can kind of get avoid having to recompute this every single time. Does everybody kind of get sense like that? So the reason why Google is willing to give you so much, you know, shortest path computations for free is not because they're willing to let you spend n squared time on them every time, okay? But because by appropriately pre-computing certain things, supplementing these shortest path algorithms with the right heuristics, okay, they can actually, reduce the, reduce the time it takes to answer individual queries. For example, you could draw a line, another way to look at this. You could draw a line across the United States. And for every road that cuts this line, you could pre-compute for any city, what is the shortest path from this to all the points that cross that line? And pre-compute the shortest path from this to any point that cuts that line. Then what is the shortest path from here to there? It's got to be the one that minimizes the distance to this plus the distance from it, okay? And so by pre-computing these kind of things, okay, they can do it more quickly, okay? Any questions about it? But at heart, what's really underlying this is a Dijkstra's algorithm, okay? Any questions about that? Any questions about homeworks or shortest paths or anything like that? Going once? Going twice? Okay, at this point, I'm willing to let you guys go, but I want you to really try to understand Floyd's algorithm as a prerequisite for for dynamic programming. Next class, we're going to shift gears to the topic of backtracking, which is one of my favorite subjects, okay? Exhaustive search through problems, but make sure you have mastered the basic graph algorithms first, okay? Anything else? If not, thanks for your attention, and I will see you guys next class.